Welcome, night owls, to Night Owl Science, the only show that lets you drift off to sleep while exploring the wildest corners of the cosmos. Tonight, we're kicking off a deep dive into the craziest, most mind-bending space facts you've ever heard. Whether you're sipping coffee at midnight or staring out the window at an inky sky, get ready for a journey through blazing plasma, gargantuan stars, and cosmic mysteries that will make your jaw drop. I'll guide you through a sequence of awe-inspiring stories, from the searing heat at the heart of our sun to star stuff so bizarre it sounds like science fiction. We'll pause between each fact for just long enough to let your brain process the magnitude of what you're hearing, then blast off into the next wonder. This episode is structured in 3 parts. First, a quick welcome and overview. Second, 8 detailed crazy facts segments. And finally, a smooth transition teasing what's coming in the next chapter of our cosmic marathon. Each fact is accompanied by vivid narration, real-time analogies, and a few rhetorical questions to keep you engaged, even as your eyelids grow heavy. So, dim the lights, put on your coziest headphones or speakers, and settle in. I recommend a warm drink, a comfortable chair, and maybe a notepad if you want to jot down your favorite fact. We're about to explore realms so extreme they defy everyday experience. And that's exactly the kind of bedtime story we do best here on Night Owl Science. All right, night owls, let's ignite our curiosity and start with fact number 1, the sun's roar. From Earth, the sun appears as a calm, yellow disk in the sky. But don't let that fool you. Its surface, called the photosphere, churns at around 5,500 degrees. That's hot enough to vaporize almost any metal you can imagine. Move deeper into its layers and temperatures skyrocket. The convective zone bubbles with plasma rising and sinking over periods of minutes, while the radiative zone beneath carries energy outward through photons that ping-pong for thousands of years before escaping. But at the core, where nuclear fusion happens, conditions defy everyday comprehension. Roughly 15 million degrees and pressures exceeding 250 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei slam into each other so frequently that the sun converts 600 million tons of hydrogen into helium every second, releasing energy equivalent to detonating 100 billion 1 megaton bombs each second. To put it in perspective, if you could somehow harness all that power for a single second, you'd power the entire United States for months. Yet the sun has maintained this furious pace for 4.6 billion years, and will continue doing so for another 5 billion, thanks to the delicate balance of gravity compressing it inward and fusion pushing it outward. Imagine compressing 1 million Earths into a sphere the size of a blow-dryer ball. That's the sun's core density. It's a roiling, unceasing nuclear reactor, invisible to our eyes but utterly essential to life on our pale blue dot. And that, night owls, is the true roar of our sun. If you think our sun is big, prepare to have your mind blown by Scuti, the largest known star in the Milky Way. Located about 9,500 light-years away in the constellation Scutum, this red supergiant has a radius roughly 1,700 times that of our sun. To visualize that, imagine replacing the sun with Scuti. Its photosphere would swallow the orbits of Mercury, Venus, Earth, Mars, and even Jupiter. You'd look up and see the star's glowing surface filling the entire sky, out to the gas giant. But Scuti is not just a pretty face. Its mass is about 30 times that of the sun, and its luminosity is nearly 500,000 times brighter. Enormous convection cells bubble up to its surface, each about the size of the Earth, causing the star's brightness to flicker over months. Despite its gargantuan size, Scuti is tenuously bound by its own gravity. Its low surface gravity means stellar material drifts away, creating a vast envelope of gas and dust that slowly erodes the star until it eventually goes supernova. The life cycle of such a behemoth is brief in cosmic terms. only a few million years. Yet its explosive death will scatter heavy elements across the galaxy, seeding future generations of stars and planets. So next time you look at the sun, remember, it's a mere pebble compared to the cosmic mountain that is OY Scooty. Could you give someone a wedding ring the size of a planet? On 55 Cancri E, you almost could. This rocky exoplanet, twice the diameter of Earth, orbits its star in under 18 hours, so close that its dayside temperature soars above 2,700 degrees. Under such extreme heat and crushing pressures, carbon in the planet's interior likely crystallizes into diamond. Some models suggest up to half of 55 Cancri E's mass could be diamond, making it a trillion carat gem floating in space. That's enough diamond to cloak the sun in sparkling brilliance. Unlike the glittering blue-white brilliance of gemstones on Earth, these diamonds would be buried under layers of molten rock hundreds of kilometers thick. Yet the concept of a diamond world has captivated astronomers and science fiction fans alike. Observations of 55 Cancri E's thermal emission show it has an ultra-thin or non-existent atmosphere, so daylight on the surface is a relentless inferno. Nightside temperatures may drop to around 1,500 degrees, allowing molten carbon to condense briefly. While no spacecraft has visited 55 Cancri E, future missions aim to probe its atmosphere and composition in greater detail, potentially confirming the diamond hypothesis. Until then, it remains one of the most tantalizing treasure planets ever discovered. Black holes are famous for swallowing light, but in 2003, astronomers made a startling discovery. They detected pressure waves emanating from the supermassive black hole at the center of the Perseus galaxy cluster. Using the Chandra X-ray Observatory, scientists observed ripples in the hot intracluster gas, sound waves generated by the black hole's periodic eruptions of material and energy. When converted from their actual frequency to one humans can hear, the notes correspond to a B-flat about 57 octaves below middle C. That is literally the deepest note in the universe. These ripples travel at several million kilometers per hour, heating the surrounding gas and regulating the cooling rate of the cluster, an essential process for galaxy formation. Without this black hole sound, gas would cool too quickly and form stars at an unsustainable rate. The fact that we can translate an astrophysical phenomenon billions of light years away into an audio signal you could play on a speaker is remarkable. It reminds us that the universe communicates in ways we're only beginning to decode. So next time someone says space is silent, tell them about the cosmic symphony playing in the heart of Perseus. It's a melody written in gravity, plasma, and X-rays, far beyond the range of human hearing, but capturable by our most advanced instruments. Not all planets have the star to call home. Astronomers estimate there are as many rogue planets wandering the Milky Way as there are stars, potentially billions of lonely worlds adrift in darkness. These planets are ejected from their birth systems by gravitational tussles or stellar flybys, casting them into interstellar space. Without a parent star, they cool rapidly. Their only heat sources are residual internal energy and radioactive decay. Rogue planets could range from Earth-sized bodies to gas giants larger than Jupiter. Some may retain subsurface oceans warmed by internal heat, offering potential habitats for exotic life forms if they have the right chemical ingredients. Detecting these nomads is challenging. They emit almost no light and are invisible against the dark backdrop of space. Microlensing surveys, which observe how a rogue planet's gravity temporarily magnifies the light of a background star, have identified a handful so far, hinting at a vast hidden population. Future infrared telescopes may uncover more of these cosmic vagabonds, revealing their distribution and origins. Imagine a world with no sunrise or sunset, orbiting nothing, bathed only in the feeble glow of its own thermal emission. A true interstellar wanderer. In 2002, astronomers attempted to determine the average color of the universe. By combining light from over 200,000 galaxies, they found an unexpected result. The universe's hue is a pale beige, nicknamed cosmic latte. You might expect a deep black or fiery red, but the mix of starlight across all wavelengths averages out to a milky, latte-like shade. This colour results from the blend of young blue stars, older red stars, and everything in between, diluted by intergalactic dust. Over cosmic time, the average colour shifts. Billions of years ago, when star formation peaked, the universe was bluer. In trillions of years, as stars die out, it will redden. But right now, we're living in a beige era. The discovery is more than a fun fact. It's a reminder that the cosmos is dynamic. Every photon streaming through space carries a story of stellar birth, death, and the vast distances between. So next time you sip your morning latte, raise your mug to the universe's official colour, a cosmic blend billions of years in the making. Falling into a black hole isn't just fatal, it's poetic. The phenomenon known as spaghettification stretches objects into thin, noodle-like strands under extreme tidal forces. As you approach the event horizon, gravity at your feet could be thousands of times stronger than at your head. This gradient rips you apart along your length, compresses you across your width, and transforms you into a one-dimensional filament. For a stellar mass black hole, this process happens well before you cross the horizon. You'd be torn apart visibly. For a supermassive black hole, the tides at the event horizon are gentler, so you might cross intact, only to be stretched violently deeper inside. Spaghettification isn't just theoretical. Simulations based on general relativity confirm that any object, star, spacecraft, or unfortunate astronaut would undergo this grotesque transformation. It's a stark example of how extreme gravity reshapes reality, turning three-dimensional bodies into cosmic pasta. Fortunately for us on Earth, the nearest black hole is over 1,000 light-years away, safe from any noodle-making mischief. Fast radio bursts, or FRBs, are one of astronomy's greatest mysteries. Millisecond-long pulses of radio energy from distant galaxies, packing as much power as the sun emits in days. The first FRB was discovered in 2007, and since then, hundreds have been recorded. Some one-off events, others repeating on irregular schedules. Their origins remain elusive. Leading theories include magnetostarquakes, colliding neutron stars, and even signs of advanced extraterrestrial technology. Recent breakthroughs have pinpointed FRBs to specific galaxies billions of light-years away, and in some cases traced them to highly magnetized neutron stars called magnetars. When a magnetar's crust cracks or its magnetic field reconfigures, it can unleash an intense blast of radio energy across the cosmos. Despite lasting mere thousandths of a second, an FRB arriving at Earth can be picked up by radio telescopes as a sharp spike, a cosmic blink that outshines all other radio sources in its sky patch. Each new detection challenges our understanding of extreme physics, and every repeating FRB gives astronomers fresh data on the environments that produce them. Are we listening to the universe's version of Morse code, or cosmic fireworks marking cataclysmic events? Either way, FRBs represent one of the most electrifying frontiers in modern astronomy. Picture two spiral galaxies, each containing hundreds of billions of stars, drifting toward each other at hundreds of kilometers per second. In roughly 4 billion years, the Milky Way and Andromeda will collide in a slow-motion ballet lasting hundreds of millions of years. From our vantage point on Earth, the night sky would transform. Andromeda would grow from a faint smudge to a glowing orb filling half the sky, its tidal arms twisting and stretching into the Milky Way's own disk. Stars themselves almost never collide. Vast distances keep them apart, but the gravitational tides would fling stars into new orbits, trigger bursts of star formation, and funnel gas toward the centers, fueling active galactic nuclei. Simulations show that the two disks would interpenetrate, warp, and eventually settle into a giant red elliptical galaxy, sometimes dubbed Milkomeda. Imagine an island of over 1 trillion stars coalescing into a single cosmic city. Even our solar system won't escape unscathed. It could be flung thousands of light years from the galactic core or captured by Andromeda's gravity. But don't worry, this grand cosmic smash-up unfolds at glacial speeds by human standards, giving you plenty of time to grab another coffee. Galactic collisions are the universe's way of remodeling itself, destroying old structures, forging new stars, and growing ever larger cosmic metropolises. It's destruction on an unimaginable scale, but in the aftermath emerges fresh potential for life's raw ingredients. When a massive star exhausts its nuclear fuel, its core collapses in a heartbeat. An event so violent it creates a shockwave ripping through the star's layers. In a matter of seconds, the star's outer envelope is blasted into space at tens of thousands of kilometers per second. The result? A supernova that can briefly outshine its entire host galaxy. Take SN 1987A, seen in 1987 in the Large Magellanic Cloud. At its peak, it shone with the brightness of 500 million suns combined. Inside that explosion, heavy elements, iron, nickel, gold, and beyond, are forged in fractions of a second through rapid neutron capture. Those elements are then flung across interstellar space, seeding future generations of stars, planets, and ultimately, life itself. In fact, every atom of iron in your blood and calcium in your bones was likely forged in a supernova over 5 billion years ago. The blast wave sweeps up surrounding gas, creating glowing supernova remnants like the Crab Nebula, an expanding shell of ionized gas and magnetic fields, still radiating strong X-rays and radio waves over a millennium later. Supernovae also regulate galactic ecosystems. Their shockwaves trigger new waves of star formation in dense molecular clouds, while their energy input helps drive galactic winds that shape the evolution of entire galaxies. When you look up at the night sky, remember that at any given moment, somewhere in the observable universe, a star is ending its life in a titanic flash you might barely glimpse with a modest backyard telescope. Neutron stars are among the densest objects in the universe, each packing more mass than our sun into a sphere just 20 kilometers across. When two neutron stars spiral together, they speed up, emitting gravitational waves in a cosmic death dance. In 2017, LIGO and Virgo detected gravitational waves from a neutron star merger, GWB 170877, and telescopes worldwide raced to observe the aftermath. The collision unleashed a kilonova, a brilliant flash of light powered by the decay of heavy elements synthesized in the merger. Models show that these mergers forge roughly half of all elements heavier than iron, including gold and platinum. In one cosmic moment, enough gold to fill all the jewelry boxes on Earth could be created. The merger also launches jets of relativistic particles, triggering a short gamma-ray burst visible across the cosmos. These bursts last less than 2 seconds, yet pack immense energy. Brief cosmic lighthouses marking sites where space-time itself ripples. Neutron star mergers teach us how gravity, nuclear physics, and extreme magnetic fields converge to create the universe's most exotic matter. And every time we detect one, we learn more about the behavior of matter at densities impossible to recreate on Earth. When you gaze at a gold wedding ring, remember, it may have originated in a cataclysmic smash-up of dead stars billions of years ago in a distant galaxy. Gamma-ray bursts, GRBs, are the universe's ultimate flashbulbs, emitting more energy in a few seconds than our sun will over its entire 10 billion year lifetime. The brightest one, GRB 080319b, became briefly visible to the naked eye across 7 billion light-years. GRBs fall into two classes: long bursts from collapsing massive stars, hypernovae, and short bursts from a neutron star mergers. In either case, tightly focused jets of gamma rays pierce through the collapsing or merging star's debris, beaming energy directly at observers lucky enough to lie in the jet's path. These jets travel at over 99.99% the speed of light, and the resulting burst can release 147 joules in under a minute. That's equivalent to converting the entire mass of our moon into pure energy via ESMC2. After the initial flash, an afterglow of X-ray, optical, and radio emission can last for days or weeks, allowing astronomers to pinpoint the burst's host galaxy and study its environment. Despite their fleeting nature, GRBs probe the early universe. Some have been detected from when the cosmos was less than 1 billion years old, illuminating the conditions of the first generations of stars. Tune in carefully, night owls. If a GRB jet ever pointed at Earth from a nearby galaxy, its gamma rays could strip our atmosphere's ozone. But don't worry, the nearest likely progenitor star is safely over 1,000 light-years away. 66 million years ago, a 10-kilometer wide asteroid slammed into what is now Mexico's Yucatan Peninsula at over 20 kilometers. The Chicxulub impact released energy equal to 10 billion Hiroshima bombs in an instant. The impact excavated a crater 180 kilometers across and sent trillions of tons of debris into the atmosphere, blocking sunlight and triggering a global impact winter. Temperatures plunged, photosynthesis halted, and over 75% of species, including the non-avian dinosaurs, went extinct. But impacts are not just ancient history. NASA's Near-Earth Object surveys track over 30,000 asteroids larger than 140 millimeters, and new telescopes keep finding smaller rocks that could still cause regional devastation. In 2013, a 20-millimeter meteoroid exploded over Chelyabinsk, Russia, with a force of 500 kilotons, shattering windows and injuring over 1,000 people from flying glass. That reminded us how vulnerable even small objects can be. To defend Earth, agencies worldwide are developing planetary defense strategies, gravity tractors, kinetic impactors, and even nuclear standoffs to nudge potentially hazardous asteroids off collision courses. The next time you see a shooting star, remember, mostly harmless dust burns up in our atmosphere, but occasionally one aims straight for the ground with world-changing force. Our sun is more than a benign light bulb. It periodically unleashes solar flares, bursts of X-rays and ultraviolet radiation, and coronal mass ejections, CMEs. Massive clouds of charged particles hurled into space. The 1859 Carrington event was the most powerful geomagnetic storm on record. Telegraph systems on Earth sparked and caught fire. Auroras lit skies at the equator, and telegraph operators reported shocks. If a Carrington-level CME struck today, it could knock out satellites, disable GPS, fry transformers, and plunge large regions into weeks-long blackouts, potentially costing trillions of dollars. NASA's Solar Dynamics Observatory and ESA's Solar Orbiter monitor the sun's active regions, giving us up to a day's warning before a CME impacts Earth. But predicting precisely which flares will produce Earth-directed CMEs remains an ongoing challenge. Meanwhile, solar storms offer scientific goldmines. Studying them helps us understand plasma physics, magnetic reconnection, and space weather interactions, knowledge crucial for protecting astronauts and our high-tech society. So the next time your phone's GPS acts up, or you glimpse unusually bright auroras far south, thank or blame the sun's explosive temperament. Some exoplanets are not serene water worlds, but infernal lava realms. Take 55 Cancri E again. Its dayside reaches over 2,700 degrees Celsius, vaporizing rock into an atmosphere of silicate vapor and sodium clouds. But the real standout is exoplanet K2-141b, which orbits its star in just 11 hours and likely has supersonic winds carrying vaporized rock from its scorching dayside to a molten nightside. There, temperatures drop enough to condense lava rains that flow like rivers across the surface. Another candidate, WASP-76b, has iron rain, titanium oxide. In its atmosphere absorbs starlight, heating one side to 2,400 degrees, vaporizing iron. Strong winds then transport the iron vapor to the cooler side, where it condenses and falls as droplets of liquid metal. Quasars are active galactic nuclei powered by supermassive black holes, gulping interstellar gas. As matter spirals in, it forms an accretion disk heated to millions of degrees, radiating prodigious energy across the spectrum. Some quasars launch jets of plasma at near light speed, relativistic fire hoses that carve cavities tens of thousands of light years across intergalactic space. In radio images, these jets appear as bipolar lobes glowing in synchrotron radiation. The most powerful quasars can outshine their host galaxies by factors of 1,000. Their radiation pressure can drive galactic winds, blowing star-forming gas out of the galaxy and quenching future starbirth. In 2020, astronomers observed rapid quasar flickering. Brightness changes over days, implying the inner accretion disk structure is far more dynamic than once thought. Some quasars even turn off and on over decades, challenging models of black hole feeding. Quasars serve as cosmic lighthouses, visible across billions of light years, probing the early universe, tracing large-scale structure, and illuminating the growth of supermassive black holes. Next time you hear of a distant quasar, imagine a cosmic earthquake visible across intergalactic space, an energetic marvel born in the darkest heart of a galaxy. Titan, Saturn's largest moon, is the only world besides Earth known to host stable lakes, and instead of water, these lakes brim with liquid methane and ethane. Surface temperatures hover around 179 degrees Celsius, cold enough that the simple molecules we call natural gas on Earth behave like water, evaporating, forming clouds, and falling as rain. Imagine towering orange skies streaked with methane clouds, then torrential showers of liquid hydrocarbons carving river channels into icy bedrock. Radar mapping by the Cassini spacecraft revealed vast seas, Ligeia Mare and Kraken Mare, each spanning over 100,000 kilometers, larger than many terrestrial Great Lakes. Titan's methane cycle mirrors Earth's hydrological cycle: evaporation from the seas, condensation into clouds, and precipitation sculpting deltas at river mouths. But the chemistry is alien. Instead of eroding silicate rock, methane rain dissolves and redeposits complex organic compounds, creating shoreline tar analogues. Beneath the methane shell, Titan likely harbors a subsurface water ocean, separated from the atmosphere by a thick ice crust. Tidal forces from Saturn knead this ocean, generating heat that may keep it liquid, and perhaps habitable for exotic life forms that metabolize methane the way Earth life uses water. In the dim orange twilight, methane lakes reflect sunlight like obsidian mirrors, and chemical reactions driven by cosmic rays and sunlight produce complex molecules, precursors to life's building blocks. Titan shows us that habitability is far broader than liquid water alone. So when you picture a lake, don't assume it's blue and benign. On Titan, a hydrocarbon sea may hide an ocean world teeming with chemistry we're only beginning to imagine. Dive 10,000 kilometers beneath Jupiter's swirling clouds, where pressures exceed 3 million bars and temperatures climb above 10,000 K. There, hydrogen, the universe's most common element, transforms from a molecular gas into a metallic fluid. In this exotic state, hydrogen's electrons roam freely, just like in a copper wire, turning the layer into a giant dynamo that generates Jupiter's enormous magnetic field, 14 times stronger than Earth's. Laboratory experiments replicate this metallic hydrogen only fleetingly, yet theoretical models predict a sea of it hundreds of kilometers thick. Metallic hydrogen challenges our definitions of solid and liquid. It behaves like a liquid metal with no fixed lattice, an alien ocean that flows beneath swirling ammonia clouds. Some theories even suggest that if you could collect it, metallic hydrogen might remain metastable at lower pressures, releasing vast energy as it reverts to molecular hydrogen. making it a potential rocket fuel of the future. Without direct probes, we infer metallic hydrogen's properties from gravitational and magnetic measurements by Juno and Galileo missions. Their data confirm a deep, electrically conducting layer consistent with metallic hydrogen, validating decades of theoretical work. Imagine a world where the ground beneath you isn't rock or ice, but a boiling sea of liquid metal hotter than the sun's surface, shaping storms, radiation belts, and auroras thousands of times stronger than Earth's. That is Jupiter's hidden underworld, accessible only to the most daring of spacecraft. Neutron stars are cosmic remnants of supernovae, ultra-dense spheres packing 1.4 solar masses into a 20 kilometer diameter. A single teaspoon of neutron star material weighs about 1 billion tons on Earth, but its outer layers form an exotic crust, unlike anything we know. This crust is a crystalline lattice of atomic nuclei, immersed in a sea of degenerate electrons and dripped neutrons. Pressures reach 1011 bar, over 1 trillion times Earth's sea level pressure, forcing nuclei to fuse into ever heavier neutron-rich isotopes in nuclear pasta phases named lasagna, spaghetti, and even gnocchi. The nuclei arrange themselves in sheets, rods, and bubbles, structures so dense and uniform that they behave like a single giant crystal spanning the entire star. These bizarre phases influence the star's thermal conductivity, magnetic field evolution, and glitch behavior. Sudden speed-ups observed in pulsar spin rates. Beneath the crust, the core may contain superfluid neutrons and superconducting protons, where frictionless flow and quantized vortices govern rotation. The interface between crust and core likely hosts exotic vortical structures that pin the crust, then unpin in sudden bursts, triggering starquakes detectable as X-ray flares. We cannot recreate neutron star crust in terrestrial labs, but by observing pulsar timing irregularities and thermal evolution, astronomers piece together its inner composition. These observations test nuclear physics at densities beyond atomic nuclei, informing our understanding of fundamental forces. So next time you hear a pulsar ticking like a cosmic clock, remember, its heartbeat originates in a crust of ultra-dense, self-assembled nuclear pasta, an environment more extreme than any material in Earth's labs. Hot Jupiters are giant gas planets orbiting within 0.05 AU of their stars, closer than Mercury is to the Sun, completing orbits in days or even hours. Exposed to intense stellar radiation, their dayside temperatures soar above 2000 degrees, inflating their atmospheres to sizes rivaling Jupiter's. Atmospheric escape rates can exceed 1012 gigauss, creating comet-like tails of hydrogen and helium tens of thousands of kilometers long. Observations of HD 29458b revealed such a tail, offering direct evidence of a planet evaporating before our eyes. Powerful winds, driven by temperature contrasts, whip gases from the dayside to the nightside at speeds over 10 km/s, redistributing heat and causing dramatic shifts in brightness as the planet orbits. High-resolution spectroscopy detects titanium oxide and vanadium oxide in some hot Jupiters, molecules that absorb starlight and create thermal inversions like a stratosphere. Some hot Jupiters exhibit unexpected temperature hotspots offset eastward, indicating super-rotating equatorial jets. Others show day-night chemical differences, with molecules like methane breaking down under intense UV flux. Their existence challenges planet formation theories. These giants likely formed beyond the ice line, then migrated inward, surviving tidal forces and intense irradiation. Yet many are inflated beyond structural models, hinting at extra heat sources, perhaps ohmic dissipation from magnetic interactions. Hot Jupiters are laboratories for extreme atmospheric physics, testing our understanding of fluid dynamics, chemistry, and radiative transfer under conditions far beyond Earth's. They They prove that planetary diversity extends to realms where no world should realistically survive. Dark matter makes up about 85% of the universe's mass, yet it neither emits nor absorbs light. It flows through us at roughly 220 km/s. Our solar system's orbital speed around the Milky Way, but remains undetectable except via gravity. Within galaxies, dark matter forms vast halos enveloping the visible disk, shaping rotation curves that stay flat instead of falling off as expected if only luminous matter were present. This discrepancy first hinted at dark matter in the 1970s and remains one of astrophysics' greatest mysteries. On Earth, we sail through a wind of dark matter particles, unimpeded by atoms. Billions pass through your fingertip every second. Experiments like Xenon 1T and Lux Zeppelin seek to catch rare collisions between dark matter particles and detector nuclei deep underground, shielded from cosmic rays. Beyond detection, dark matter's velocity distribution reveals clues about its origin, a smooth halo component interspersed with streams from disrupted dwarf galaxies. Observations of stellar streams, like those from the Sagittarius dwarf galaxy, map these dark matter flows, helping refine detection strategies. Future directional detectors aim to measure both energy and incoming particle direction, seeking an unmistakable signature of the Earth's motion through the halo. Should we catch dark matter's wind, it would revolutionize particle physics and cosmology, identifying the invisible scaffold on which galaxies build. So while we can't see dark matter or feel it, it shapes everything from galaxy formation to local particle interactions, proof that the universe's most important substance lies beyond our senses. Mercury, the solar system's innermost planet, swings as close as 46 million kilometers to the Sun, about 1.31 AU, and then retreats to 70 million kilometers at aphelion. This eccentric orbit produces surface temperatures ranging from 180 degrees at night to 430 degrees during the day, a swing of over 600 degrees every 88 hours. Without a substantial atmosphere to redistribute heat, Mercury's dayside bakes beyond the melting point of many metals, while the night side plunges to cryogenic temperatures. Messenger's infrared mapping revealed cold traps, impermanently shadowed craters at the poles, where water ice persists despite the sun's glare. These polar ice deposits, tens of meters thick in places, likely originated from cometary and asteroidal impacts, then migrated to the shadows. Radar reflections confirm bright patches within craters like Prokofiev, making Mercury the only planet besides Earth with stable surface ice. Mercury's exosphere, an ultra-thin atmosphere of sodium, potassium, and calcium atoms, forms when solar wind and micrometeoroids liberate atoms from the surface. This tenuous shroud shifts with Mercury's distance to the Sun, creating transient tails of sodium light detected by ground-based telescopes. Compasses carried on NASA's Mariner 10, and Messenger revealed Mercury's magnetic field, about 1% of Earth's, generated by a partially molten iron core, twice as big proportionally as Earth's. Even in such extreme heat, the core retains enough fluidity to drive a dynamo. Mercury's orbit also precesses due to general relativity, an effect first confirmed by observing its perihelion advance, one of the classic tests of Einstein's theory. This little planet continually reminds us that extreme proximity to a star yields extremes in temperature, geology, and fundamental physics. In the constellation Centaurus lies the Boomerang Nebula, the coldest natural place known, chilling to just 1 K, colder than the 2.7 K cosmic microwave background. How does it get that cold? A dying red giant star expels gas at 164 km. As this gas expands into space, it cools through the Joule-Thomson effect. The nebula's hourglass shape, a symmetric pair of lobes, suggests collimated outflows sculpted by magnetic fields or companion interactions. Inside, gas temperatures drop to more 272 degrees Celsius, so cold that molecules freeze out, forming tiny grains that scatter light and give the nebula its ghostly glow. Infrared observations reveal dust filaments tracing shock fronts, while ALMA's high-resolution imaging maps velocity gradients, confirming rapid expansion driving the cooling. The Boomerang Nebula shows that, contrary to intuition, expanding gas can chill below the ambient temperature of space itself. This cosmic cryogenic lab offers insight into late stages of stellar evolution and the physics of gas cooling, processes relevant to star formation in molecular clouds as well. And its ethereal beauty makes it a favorite target for astrophotographers chasing the universe's extremes. The next time you crank your freezer to power 30 degrees, be grateful. It's nowhere near as cold as the Boomerang Nebula's airy exhalation from a dying star. Venus's surface pressure is about 92 bar, equivalent to lying under 900 meters of ocean on Earth. Drop a lander there, and its instruments implode within minutes under crushing weight. This enormous pressure arises from Venus's dense, CO2-rich atmosphere, overlaid with clouds of sulfuric acid. Weather balloons would be crushed long before reaching the ground, but at about 50 kilometers altitude, pressure and temperature match Earth's, an enticing region for future aerial platforms. Below that cloud deck, temperatures hover around 465 degrees Celsius, hot enough to melt lead, and corrosive acid rains that evaporate before reaching the surface. The combined heat and pressure accelerate chemical reactions, scrambling surface rocks into unfamiliar minerals. Venera landers from the Soviet era survived only about an hour on the surface, yet returned valuable images of jagged volcanic plains and pancake domes, evidence of widespread volcanism. Recent radar data hint at active lava flows, suggesting Venus may still be geologically restless. Understanding Venus's extreme greenhouse environment helps us model runaway climate scenarios, both for exoplanets and for our own planet's future. Venus stands as a cautionary tale. When pressure, temperature, and chemistry combine in extremes, a world transforms into an inferno under layers of toxic shroud. Cosmic strings are hypothetical filaments of energy thought to form in the early universe, akin to cracks that appear when water freezes into ice. According to grand unified theories, as the nascent cosmos cooled and symmetries broke, these one-dimensional defects could have been left behind, stretching across billions of light years, but thinner than a proton. Despite their microscopic width, on the order of 10 to 29 centimeters, the mass per unit length of a cosmic string is staggering, roughly 1021 kilograms per meter. That's equivalent to the mass of Mount Everest crammed into a thread narrower than an atomic nucleus. Their immense tension would warp space around them, creating a conical geometry that could bend light like a cosmic prism. If a cosmic string passed between us and a distant galaxy, we might see double images of that galaxy, perfectly identical and separated by a fixed angle, an unmistakable signature, unlike any other lensing by stars or galaxies. Moreover, loops of cosmic string would oscillate, emitting bursts of gravitational waves as they snap and reconnect, analogous to plucking a violin string, but resonating across the fabric of space-time. Pulsar timing arrays and gravitational wave detectors like LIGO and the upcoming LISA mission are hunting for these telltale ripples. Although no definitive detection has been made, tantalizing hints in the timing residuals of millisecond pulsars and unexplained gravitational wave backgrounds keep the search alive. Finding a cosmic string would provide a direct glimpse into physics at energies far beyond terrestrial colliders, unlocking secrets of the universe's first trillionth of a second. Until then, cosmic strings remain a captivating bridge between cosmology and particle physics, threads of possibility weaving through our understanding of space-time itself. If black holes are cosmic sinkholes, white holes are their theoretical opposites, regions that can only eject matter and energy, never absorb anything. In solutions to Einstein's equations, a white hole emerges as the time reverse of a black hole, spitting out the contents that might have fallen in elsewhere. Unlike black holes, which cloak themselves behind event horizons, white holes would be naked singularities, visible but forever unapproachable. Any object trying to enter would be repelled by infinite tidal forces at the horizon. Their existence remains purely mathematical. No astrophysical process is known to form one in our universe. Some speculative models of quantum gravity and loop quantum cosmology propose that a black hole's collapse could rebound as a white hole, releasing trapped information in a final explosion, a possible resolution to the black hole information paradox. If so, tiny primordial black holes might pop as white holes today, producing brief, high-energy bursts we could detect as gamma-ray flashes. Observationally, astronomers have monitored fast gamma-ray spikes and high-energy neutrino events, searching for patterns inconsistent with known astrophysical sources. While none have definitively matched white hole predictions, ongoing surveys by Higgs, IceCube, and the Fermi Gamma-Ray Space Telescope keep the door open. A confirmed white hole would revolutionize our view of space, time, and the ultimate fate of information in the cosmos, turning a theoretical curiosity into a cornerstone of quantum gravity. Until then, white holes remind us that even the most exotic solutions to general relativity may one day find a home in observational astronomy. In the early 2000s, teams led by Alexander Kashlinsky uncovered a puzzling phenomenon. Galaxy clusters across hundreds of millions of light years appeared to stream toward a single patch of sky at speeds up to 1,000 km/s. They dubbed this unexplained motion the dark flow, since it couldn't be accounted for by the gravitational pull of known structures in the observable universe. Using a minute temperature anisotropies in the cosmic microwave background, the kinematic Sunyaev-Zeldovich effect, they measured cluster velocities relative to CMB rest, finding a coherent drift over scales far larger than our local supercluster. If confirmed, dark flow suggests influence from mass concentrations beyond our observable horizon, or hints at new physics such as modifications to gravity on the largest scales. Subsequent studies have produced mixed results. Some confirm a weak flow, others attribute the signal to systematic errors or statistical flukes. The debate continues as Planck data and larger cluster catalogues refine measurements. If dark flow persists, it could imply that our cosmic neighborhood is being tugged by structures in a multiverse beyond our view, or that the initial conditions of the Big Bang contained large-scale anisotropies never erased by inflation. Whether a cosmic mirage or a glimpse beyond the horizon, dark flow challenges the cosmological principle of large-scale uniformity and invites us to consider a universe more vast and stranger than we ever imagined. While dark flow hints at unseen mass beyond our sight, the Great Attractor is a nearby gravitational mystery, drawing our local group toward the constellation Centaurus at about 600 km/s. Discovered in the 1970s via peculiar galaxy velocities, this massive region lies roughly 150 million light-years away, partially obscured by the Milky Way's disk. Early surveys revealed a gravitational pull inconsistent with visible galaxy distributions. Star count studies through the zone of avoidance later identified the Norma cluster and the Shapley supercluster as major contributors, but still fell short of the total mass required. The Great Attractor may be part of an even larger superstructure, Laniakea itself, which redefined our home supercluster in 2014. Within this framework, the Great Attractor sits near the basin of attraction for tens of thousands of galaxies streaming toward a common center. X-ray observations by ROSAT and infrared mapping by IRIS penetrate galactic dust, revealing hot gas and hidden galaxies that add to the mass budget. Yet some dark matter component may remain unaccounted for, lurking in filaments or as diffuse gas. Understanding the Great Attractor isn't just about charting our cosmic address. It sheds light on how superclusters assemble, how dark matter congregates on large scales, and how the universe's structure evolves. We may never see the full picture through our dusty galactic plane, but each new survey brings us closer to mapping the true architect behind our galaxy's grand cosmic motion. In October 2017, astronomers spotted Oumuamua, an object on a hyperbolic orbit passing through our solar system, the first confirmed interstellar visitor. Unlike typical comets, it showed no visible coma, yet exhibited non-gravitational acceleration, inconsistent with pure gravity, sparking intense debate. Its elongated, cigar-shaped form, inferred from its light curve, suggested an aspect ratio of at least 5.1, unlike any asteroid or comet seen before. Was it a rocky fragment ejected from another star system, or a thin, sheet-like sail propelled by solar radiation pressure, as some speculated when fringe theories proposed alien technology? Follow-up observations by Spitzer failed to detect infrared emission, imposing strict upper limits on its size and reflecting a surface at least 10 times darker than charcoal. Subsequent analysis favored outgassing of molecular hydrogen as the driver of its weird acceleration, though direct gas detection remained elusive. Oumuamua's discovery triggered new survey strategies. The Pan-STARRS telescope detected it, but next-generation observatories, like the Vera C. Rubin Observatory, will find interstellar interlopers by the dozens each year, allowing rapid, spectroscopic follow-up and possibly even intercept missions. Whether natural rock or alien probe, Oumuamua opened our eyes to a galaxy teeming with wandering debris and reminded us how little we know about our interstellar neighborhood. In 2015, Kepler data revealed KIC 8462852, later dubbed Tabby's star, undergoing irregular, aperiodic dips in brightness up to 22%. No known exoplanet or binary companion could explain the erratic dimming profile. Initial speculations ranged from swarms of comets to circumstellar dust clouds. The most sensational hypothesis proposed a partial Dyson swarm, megastructures built by an advanced civilization harvesting stellar energy. Multi-wavelength observations have since largely ruled out large opaque objects, favoring uneven dust distributed on highly eccentric orbits, possibly originating from a shattered planet or exocomet breakup. Infrared surveys found no corresponding excess heat, challenging simple dust models and suggesting the obscuring material must be cold or transient. Long-term photometry shows gradual dimming over decades, while spectroscopic monitoring captures variable absorption lines, indicative of gas clouds crossing the star's face. Computer simulations of dust dynamics and planetary disruption reproduce many features, but a comprehensive model remains elusive. Tabby's star stands as a testament to the surprises hidden in precise stellar monitoring, and a reminder that extraordinary claims demand extraordinary evidence. Whatever the cause, the star's strange behavior ignited public imagination and forged a new subfield of citizen science monitoring, where amateurs and professionals jointly track stellar oddities in real time. Approaching a black hole isn't just dangerous, it warps your experience of time itself. According to general relativity, clocks nearer a massive object tick more slowly relative to distant observers, a phenomenon known as gravitational time dilation. For a Schwarzschild, non-rotating black hole, the time dilation factor at a radius r is given by 1 to 2 gm rc2. At the event horizon, r equals 2 gm c2, this factor drops to 0. To a distant observer, infalling clocks appear to freeze at the horizon indefinitely. In lay terms, if you hovered just outside the horizon of a 10 solar mass black hole, 1 second for you would correspond to years back on Earth. Conversely, from your vantage, the entire future of the universe might unfold in moments. In the film Interstellar, the planet near the supermassive black hole Gargantua experiences an hour equating to 7 years on Earth. a dramatization based on scientific consultation, but pushing the limits of realistic parameters. Realistically, tidal forces near stellar mass black holes would spaghettify you before you could linger near the horizon. Observationally, gravitational redshift of light escaping from white dwarfs and neutron stars confirms time dilation effects. Pulsar timing also reveals tiny delays consistent with general relativity. Future space-based atomic clocks could measure time dilation around Earth's gravity with unprecedented precision, testing relativity at new levels. Time dilation near black holes illustrates how mass and motion weave together space and time, and how gravity can stretch not just distances, but the very flow of existence. On the grandest scales, matter in the universe arranges itself into a vast cosmic web. Filaments of galaxies and dark matter stretching hundreds of millions of light years, separated by enormous voids. This structure emerged from tiny density fluctuations in the primordial plasma, amplified by gravity over 13.8 billion years. Galaxy redshift surveys like SDSS and 2DF have mapped the three-dimensional distribution of millions of galaxies, revealing a sponge-like network with dense knots, galaxy clusters, thread-like filaments, and cavernous voids. Supercomputer simulations of LCDM cosmology reproduce this web remarkably well, validating our model of dark matter and dark energy. Gas flows along filaments into cluster nodes, fueling star formation and black hole growth. Observations of the intergalactic medium via the Lyman O forest, absorption lines in quasar spectra, trace tenuous hydrogen gas in filaments too faint to image directly. At filament intersections, the environment is rich. Galactic mergers, active galactic nuclei, and shock-heated gas create X-ray bright regions. Meanwhile, voids expand faster than the average universe, influencing galaxy evolution in isolation. The cosmic web underpins every galaxy's context, dictating how matter accretes, how galaxies cluster, and how the universe's large-scale geometry unfolds. It is both a skeleton and a stage for cosmic evolution, an immense tapestry woven by gravity's subtle hand. Beneath Saturn's serene rings lies a bizarre weather cycle, liquid helium rain. At depths where pressures exceed 1 million times Earth's atmosphere, hydrogen becomes metallic and forces helium to separate out. This helium then condenses into droplets, akin to oil separating in a vinaigrette, and plummets through the liquid metal hydrogen layer. Each falling droplet releases gravitational potential energy as heat, explaining why Saturn emits about twice as much thermal radiation as it absorbs from the Sun. Cassini's gravity and radio science data revealed a depletion of helium in the upper atmosphere consistent with this helium rain. Meanwhile, ring seismology, studying ripples in Saturn's rings, detects subtle oscillations driven by internal layering, confirming precipitation zones deep within the planet. Imagine storms where raindrops are lighter than Earth's air and cascade into a glowing inferno below. That's Saturn's hidden climate, a reminder that even familiar worlds can harbour truly alien meteorology. Meet K2229b, a super-Mercury 480 light-years away. With 1.2 Earth radii, but 2.6 Earth masses, its density near 10 implies a core, comprising about 70% of its mass, far denser than Earth's 32% iron core. Astronomers believe intense stellar radiation and tidal forces stripped away its silicate mantle, leaving behind a metal heart. TESS and Cheops transit plus radial velocity measurements pin down its mass and radius, while spectral analyses show a lack of volatiles and silicates. At just 0.012 AU from its star, its dayside temperature soars above 2000 degrees, hot enough to keep residual rock molten over an iron sphere. K2229b challenges our models of planet formation, hinting at a population of ultra-dense, metal-rich exoplanets that defy Earth-centric geology. Super-Earths, planets between 1 and 10 Earth masses, are among the most common exoplanets, yet our solar system has none. They span slightly larger than Earth, up to twice Earth's diameter, with surface gravities from 1.5x to 2.5x Earth. Some, like LHS 1140b, lie in habitable zones with temperate climates. Others bake under blistering irradiation. Their compositions range from superpuffs, with light gas envelopes, to water worlds with global oceans hundreds of kilometers deep, or rocky super-Earths with basaltic mantles and iron cores. The TRAPPIST-1 system's 7 Earth-size worlds, including 3 in its habitable zone, showcase this diversity. By combining mass radius measurements with interior structure models, astronomers infer composition. Upcoming JWST observations will probe super-Earth atmospheres for biosignature gases, oxygen, methane, and beyond, bringing us closer to answering which of these worlds could host life. Not a planet, but a world unto itself. The Soap Bubble Nebula, Able 78. This glowing shell spans 2 light years, encasing a dying star that ejected its outer layers in a spherical blast. Ultraviolet light from the exposed hot core ionizes oxygen and hydrogen, painting the nebula in ghostly greens and blues. Hubble images reveal intricate filaments and knots, sculpted by magnetic fields and shockwaves. A late helium shell flash created multiple ejection phases, layering the nebula's shell. The result, a near-perfect cosmic bubble, rippling with sound wave oscillations, stellar pulsations frozen in time. The Soap Bubble Nebula reminds us that even stars build wondrous planets when they die, crafting ethereal worlds of gas and light. Voyager 2's 1989 flyby revealed Triton, Neptune's largest moon, spouting dark nitrogen plumes hundreds of kilometers high. In southern summer, sunlight penetrates translucent nitrogen frost, heating darker subsurface layers until gas pressure bursts through cracks. Plumes carry dust grains that form twin, dark jets, contrasting with Triton's pale terrain. These geysers sculpt cantaloupe terrain of pits and ridges, continually renewing the surface. Spectroscopy identifies mostly nitrogen with traces of methane and CO, hinting at a subsurface ocean warmed by tidal heating. Triton's cryovolcanism inspires comparisons to Enceladus and Europa, other ocean worlds where icy eruptions may hint at life-sustaining environments. Io, Jupiter's innermost Galilean moon, is the solar system's volcanic hotspot. Over 400 active volcanoes dot its surface, fueled by tidal friction from Jupiter and neighbouring moons. Loki Patera and Pele host vast lava lakes glowing in infrared at temperatures above 1600 Celsius, hotter than many terrestrial lavas. Sulfur dioxide plumes tower hundreds of kilometers, depositing sulfurous frost that paints Io in reds, yellows, and blacks. Over time, lava flows reflood older terrain, while lake crust sinking events trigger dramatic thermal brightening. Studying Io teaches us about tidal heating, magma differentiation, and sulfur volcanism, vital processes for understanding both Earth and exoplanetary geology under extreme stresses. Chthonian planets are the stripped cores of former hot Jupiters. Intense stellar radiation and tidal forces erode their hydrogen-helium envelopes over billions of years, leaving behind rocky remnants. Kepler-52b orbits so close its atmosphere has likely vaporized, revealing a densified rocky core. Without a gas shield, its exposed crust bakes under intense UV radiation, potentially forming a scorched iron-rich surface. These ghostly worlds can masquerade as super-Earths, but their extreme densities and orbits betray their giant planet origins. Future spectroscopy during transit may detect residual exospheres, hydrogen or helium ghosts, confirming their chthonian nature. Chthonian planets exemplify stellar irradiation's power to obliterate worlds, sculpting exotic end states for gas giants. As stars like our Sun expand into red giants, they engulf close-orbiting planets. Gaia and Apogee surveys find red giants with lithium enhancements, lithium being swiftly destroyed in stellar cores, suggesting recent planet ingestion. Some evolved stars spin faster than expected, a sign of angular momentum transfer from swallowed planets. Infrared excesses point to dusty debris disks from evaporated planetary material. In dramatic cases, star-planet mergers spark red novae, as witnessed in V838 Monocerotis in 2002, a luminous outburst likely from a companion's engulfment. Studying these events reveals the ultimate fate of inner planets, including our own in roughly 5 billion years, and how planetary building blocks recycle into stellar atmospheres. Our local group, which includes the Milky Way, Andromeda, and dozens of dwarf galaxies, resides within the Virgo supercluster, a vast assembly of over 100 galaxy clusters, stretching some 110 million light-years across. At its heart sits the Virgo cluster, containing more than 2,000 galaxies bound by gravity. First mapped in the 1950s by Gérard de Vaucouleurs, this supercluster was once thought to be the ultimate cosmic neighborhood. Yet deeper surveys revealed it's just one node in an even larger structure called Laniakea. Within Virgo, galaxies exhibit complex motions. Spirals like our own hug the outskirts, while massive ellipticals dominate the dense core. The cluster's intracluster medium, hot, X-ray emitting gas at tens of millions of degrees, holds more mass than all its galaxies combined, and ram pressure stripping quenches star formation in infalling members. Using redshift surveys, astronomers map Virgo's three-dimensional shape and velocity flows, observing how nearby groups steer toward its gravitational center at hundreds of kilometers per second. Despite its immense scale, Virgo's influence is local. Its gravity helps define the boundary of our local group's motion. From here, we see that even local in cosmic terms spans hundreds of millions of light-years and contains mass measured in quadrillions of suns. In 2003, data from the Sloan Digital Sky Survey unveiled one of the universe's largest known structures, the Sloan Great Wall. Stretching over 1.37 billion light-years, this filamentary ridge of galaxies spans a tenth of the observable universe's diameter. Composed of multiple superclusters and galaxy walls, it forms a tangled web of galaxy-rich zones, separated by vast voids. Its discovery challenged assumptions about the largest possible cosmic structures, pushing the scale at which homogeneity emerges. The Sloan Great Wall's galaxies are catalogued by their redshifts, grouping into clusters like Coma and Hercules. Spectroscopic studies show variation in galaxy types along its length. Denser regions harbour more ellipticals, while filaments favour spirals and starbursts. Simulations of LCDM cosmology reproduce similar walls when seeded with inflationary fluctuations, affirming that these colossal structures arise naturally from gravitational growth. Yet the Sloan Great Wall remains a stunning visual reminder that galaxies aren't scattered randomly. They trace a hidden skeleton of dark matter and gas, converging into walls that span the cosmos. The cosmic microwave background, CMB, is the universe's oldest light, a faint afterglow from 380,000 years after the Big Bang, now cooled to 2.725 Vk. Mapped in exquisite detail by Kobe, WMAP, and Planck, the CMB encodes temperature fluctuations at the 10 microkelvin level. These tiny anisotropies correspond to density variations, seeds of all cosmic structure. Over 13.8 billion years, gravity amplified these primordial ripples into galaxies, clusters, and the filamentary cosmic web. The CMB also reveals the universe's geometry and composition. Its angular power spectrum's peaks and troughs measure the relative densities of dark energy, dark matter, and baryons, confirming a flat universe dominated by dark energy. Regions slightly hotter than average indicate compressed plasma, later forming galaxy clusters. Cooler spots mark rarefied zones that evolved into cosmic voids. By studying the polarization of the CMB, cosmologists hunt for signatures of primordial gravitational waves, direct evidence for inflation, the exponential expansion that smoothed the early cosmos. Thus, the CMB is both our backlit blueprint and our horizon, the ultimate large-scale snapshot of the universe's infancy, still shaping structure today. In 2014, a team led by R.B. Tully redefined our cosmic address with Laniakea, the immense heavens supercluster spanning over 520 million light-years. Laniakea encompasses Virgo, Hydra Centaurus, and dozens of other clusters, bound together by a common gravitational flow. By mapping galaxy velocities using the Cosmic Flows 2 catalogue, they identified a basin of attraction. All galaxies within its watershed drift toward a central region near the Norma cluster. Laniakea's boundary is defined not by arbitrary redshift cuts, but by flow lines, like river basins on Earth, racing toward the supercluster's gravitational heart. Within Laniakea reside roughly 100,000 galaxies, with a total mass exceeding 10 to 17 solar masses. This redefinition demonstrates that superclusters are not static collections, but dynamic flow zones. Our local group's motion toward the great attractor lies comfortably within Laniakea's domain. Laniakea underscores how interconnected cosmic structures are, each galaxy swimming in the currents of gravity, guided by unseen dark matter filaments beneath the surface. Galaxies and clusters are embedded in vast halos of dark matter, an invisible scaffold containing about 85% of all matter. These halos extend far beyond visible stars, shaping rotation curves and stabilizing orbits. Simulations like the Millennium Run show that dark matter halos merge hierarchically. Small halos coalesce into larger ones, producing substructure within galaxy clusters, satellite galaxies and streams marking past mergers. Observations of gravitational lensing, where foreground halos bend light from background galaxies, map the 3D distribution of dark matter. Bullet cluster studies famously separated dark matter from hot gas during a collision, providing direct evidence that most mass doesn't interact electromagnetically. Dark matter halos set the stage for galaxy formation. Baryonic matter falls into these wells, cools, and forms stars. The halo's concentration and spin influence a galaxy's morphology, disk versus elliptical. Despite decades of study, the nature of dark matter particles remains unknown. Searches span direct detection experiments deep underground, indirect searches for annihilation signals in the galactic center, and collider production at the LHC. Until we identify dark matter's particle, its halos stand as silent architects of cosmic structure, shaping the cosmos we see while eluding detection. After the cosmic dark ages, the first stars and galaxies emitted ultraviolet light that reionized neutral hydrogen, transforming the universe from opaque to transparent. This epoch of reionization unfolded between 400 million and 1 billion years after the Big Bang. Ionized bubbles formed around galaxies and quasars, growing and merging until only neutral islands remained. Observations of high redshift quasars, Gunn-Peterson troughs, reveal when reionization completed around Z6. 21 centimeters experiments like LOFAR and the upcoming SKA target the redshifted hydrogen line, aiming to map the three-dimensional topology of these ionized bubbles. By measuring radio fluctuations, astronomers hope to watch reionization's patchwork stitch the early universe together. Simulations show bubble sizes ranging from a few million to tens of millions of light years, depending on galaxy clustering and photon escape fractions. Understanding reionization bubbles illuminates how the first galaxies formed, how they emitted ionizing photons, and how feedback regulated early star formation, providing a missing chapter in cosmic history. Between filaments lie cosmic voids, vast regions tens to hundreds of millions of light-years across, containing only a few galaxies per cubic gigaparsec. Voids expand faster than denser regions, acting as cosmic accelerators under dark energy's influence. Voids under density makes them pristine laboratories for cosmology. Galaxy motions within voids directly probe dark energy and modified gravity theories. Surveys like DESI and Euclid will measure void shapes and dynamics across cosmic time. Inside voids, galaxy formation is suppressed. Dwarf galaxies that do form exhibit unusual properties: low metallicity, high gas fractions, and late star formation histories. Studying void galaxies tests how environment shapes galaxy evolution. At void centers, the CMB may show cold spots, integrated Sachs-Wolf effects, where photons climbing out of underdense wells lose energy. These subtle signals help constrain cosmological parameters. Though often overlooked, voids occupy most of the universe's volume, making them a dominant factor in its expansion and evolution. The Bullet Cluster 1E0657-56 is a cosmic car crash. Two galaxy clusters collided at over 3,000 km/s, separating dark matter from hot gas. X-ray images reveal a bullet-shaped shock front in the intra-cluster medium, while weak lensing maps show the majority of mass leading the gas. This separation provides direct evidence that dark matter interacts only gravitationally, placing tight limits on its self-interaction cross-section. The shock's Mach III bow wave heated gas to 100 million K, glowing brightly in X-rays, while galaxies, collisionless, sailed through mostly unscathed. Bullet cluster studies inform both astrophysics and particle physics. They demonstrate how structure assembles, how dark matter behaves under extreme conditions, and how shocks accelerate cosmic rays, emitting radio relics at cluster edges. As a cosmic laboratory, the Bullet Cluster remains one of the clearest proofs of dark matter's existence and properties. Launched in December 2021, the James Webb Space Telescope, JWST, carries a 6.5-meter segmented mirror and infrared instruments designed to see the first galaxies and probe exoplanet atmospheres. In its first 18 months, JWST pinpointed water vapor in the atmospheres of several hot Jupiters, and even detected hints of carbon dioxide and clouds on temperate mini-Neptunes. Spectral fingerprints impossible for previous telescopes to resolve. In deep field observations, JWST pushed back the cosmic frontier to just 250 million years post-Big Bang, revealing galaxies surprisingly massive for their age, and challenging our models of early star formation. Embedded within those nascent galaxies, astronomers identified stellar nurseries and mapped how dust shapes galaxy growth. Webb's NIR-SPEC and MIRI instruments also delivered census-level surveys of methane in the Saturnian system, faint emission lines from distant quasars, and stunning maps of star-forming regions obscured by dust in the Milky Way. Its sunshield and L2 halo orbit keep temperatures below 50 K, allowing sub-Kelvin sensitivity to detect the faintest glimmers of the early universe. Every month, new JWST papers rewrite textbooks, its spectra revealing complex chemistry in protoplanetary disks, its images dissecting the role of feedback in galaxy evolution, and its time domain programs capturing exploding supernovae in the distant cosmos. With at least a decade of scientific operations ahead, JWST stands as the torchbearer for exoplanet climatology and cosmology, ushering in an era where we characterize worlds for habitability and trace cosmic dawn with unmatched clarity. NASA's Europa Clipper, set to launch in October 2024, will perform over 40 close flybys of Jupiter's icy moon Europa from a highly elliptical orbit. Equipped with cameras, ice-penetrating radar, magnetometers, and a neutral gas ion mass spectrometer, Clipper will map surface fractures, measure the thickness of Europa's ice shell, and probe the underlying ocean's salinity and depth. Each flyby will approach within 25 kilometers of the surface, resolving features as small as 5-meter emission and detecting plumes that spout water vapor into space. By studying induced magnetic fields, the magnetometer will constrain the ocean's conductivity, key to assessing whether it's a global liquid layer or a series of subsurface pockets. Radar pulses will penetrate up to 30 kilometers of ice, revealing internal layering, brine pockets, and potential convection plumes, offering the first X-ray of Europa's frozen lid. Spectral images will map organic compounds and salt distribution, testing hypotheses about exchanges between the ocean and surface. Crucially, Clipper's data will inform future land emissions by pinpointing safe, yet scientifically rich landing zones where biosignatures might be deposited by plume fallout. Europa. Clipper represents humanity's best shot at confirming a habitable environment beyond Earth, an icy world that may harbour the ingredients for life beneath its cracked shell. NASA's Artemis program aims to return humans to the lunar surface by 2026 and establish a sustainable presence by the early 2030s. Artemis 1 and 2 will test the Space Launch System, SLS, and Orion crew capsule, leading to Artemis III's landing near the lunar South Pole, a region rich in water ice deposits within permanently shadowed craters. Following initial landings, the Gateway mini space station in lunar orbit will serve as a staging point for crewed expeditions and scientific operations. International and commercial partners plan to contribute modules for habitation, refueling, and robotics. On the surface, NASA envisions an Artemis base camp with inflatables, 3D printed habitats using regolith, and mobility systems like rovers and hoppers. Solar-powered systems will extract water from ice deposits for life support and rocket propellant, enabling deep space missions to Mars and beyond. Scientific objectives include geologic sampling of polar volatiles, seismic studies of the lunar interior, and radio astronomy experiments shielded from Earth's interference on the far side. Artemis represents not just a return to the moon, but the first step toward a cis-lunar economy, mining, manufacturing, and tourism in Earth's backyard, paving the way for crewed Mars missions and permanent settlements. NASA's Dragonfly mission, scheduled to launch in 2027 and arrive at Saturn's moon Titan in 2034, will deploy an autonomous dual quadcopter to fly between high-priority sites on the organic-rich surface. Titan's dense atmosphere, 1.5 the bar, and low gravity, 0.14 g, make it an ideal location for aerial exploration, enabling Dragonfly to scout sites for prebiotic chemistry. Dragonfly carries mass spectrometers, a gamma-ray spectrometer, meteorology sensors, and a seismometer to measure tectonic activity. It will land near dune fields to sample organics, then fly dozens of kilometers to revisit potential impact sites and liquid methane-ethane lakeshores, searching for chemical signatures of life's precursors. Powered by a multi-mission radioisotope thermoelectric generator, MSRTG, Dragonfly can operate through Titan's frigid nights and seasons, conducting seismic surveys that probe the interior structure. Its adaptive flight software will navigate GPS-free skies, avoiding hazards and optimizing science returns. Dragonfly opens a new paradigm in planetary exploration, roaming worlds by air rather than rolling or waddling, bringing us closer to unraveling how life's building blocks form in exotic ocean worlds. Concept studies at NASA's Johns Hopkins APL and the Initiative for Interstellar Studies are developing interstellar probe architectures capable of reaching the heliopause within 25 years and interstellar space within 50. Proposed methods include solar sail missions that dip close to the sun for a sundiver acceleration, achieving velocities up to 100 km/s, or fusion-powered beamed energy sails propelled by ground-based lasers. The interstellar probe concept would carry instruments to map the heliosphere's boundary, sample local interstellar medium properties, and measure galactic cosmic rays unfiltered by solar wind. Small-sat architectures harness CubeSat swarms, piggybacking on larger missions, testing high-power solar sails and deep space laser communications. Advances in lightweight materials, AI guidance, and autonomous fault management are critical for journeys spanning decades and distances beyond 1,000 AU, while formidable challenges remain: radiation shielding, power longevity, and communication delays. The prospect of sending the first human-made vehicle into the nearby stars is driving innovations in propulsion, miniaturization, and mission design. Detecting and characterizing Earth-like exoplanets requires direct imaging instruments with starlight suppression factors exceeding 1010. Concept studies for next-generation flagship missions, HabEx and LUVOIR, propose 4 to 15 meter space telescopes equipped with coronagraphs and external starshades to block parent stars' glare. Starshades, 100 mm diameter occulters flying tens of thousands of kilometers from the telescope, could enable multi-wavelength imaging and spectroscopy of dozens of habitable zone worlds, searching for biosignatures like oxygen, ozone, and vegetation red edge. LUVOIR's segmented mirrors and sensitive spectrographs would also survey protoplanetary disks and characterize giant planet atmospheres, while HabEx prioritizes cost-effective design for exo-Earth yield. Combined with high-contrast adaptive optics, deformable mirrors, and wavefront sensing, these missions aim to deliver reflected light spectra revealing surface composition, cloud cover, and even seasonal changes, transforming exoplanet science from statistical surveys to detailed comparative planetology. LIGO and Virgo's groundbreaking detections of gravitational waves have opened a new window on the universe. Next-generation ground detectors, Cosmic Explorer in the US and Einstein Telescope in Europe, will extend sensitivity tenfold, probing black hole and neutron star mergers across most of cosmic history. In space, the Laser Interferometer Space Antenna, LISA, planned for the 2030s, will consist of 3 spacecraft forming a 2.5 million kilometer equilateral triangle, measuring low-frequency waves from supermassive black hole binaries and extreme mass ratio in spirals. These detectors will map the universe's structure via standard sirens, offering independent measurements of the Hubble constant and insights into dark energy. They will also reveal stochastic backgrounds from cosmic strings or primordial turbulence, potential signatures of new physics at the universe's dawn. Gravitational wave astronomy will evolve from a novelty to a precision tool, charting the universe's mass distribution, testing general relativity in strong fields, and potentially detecting signals from the earliest moments after inflation. Space-based solar power, SBSP, envisions giant photovoltaic arrays in geostationary orbit, converting sunlight, unobstructed by atmosphere or night, into electricity beamed to Earth via microwaves or lasers. Concepts like Japan's SPS Alpha and Northrop Grumman's Space Solar Power Exploratory Research and Technology (CERT) program are developing lightweight, foldable panels and high-efficiency wireless power transmission. A single 1 GW orbital solar plant could deliver continuous baseload power to grid stations, reducing carbon emissions and enhancing energy security. Key challenges include launch cost reduction, thermal management, and precise beam pointing to ensure safety. International collaborations and private ventures are funding technology demos, small-scale wireless power beaming experiments and modular satellite buses, aiming for orbital prototypes by the 2030s. SBSP represents a visionary fusion of space technology and sustainable energy, promising to harness the sun in Earth orbit to power our civilization below. First, the sheer scale of the universe demands humility. In 40 minutes, our light could travel from Earth to the sun and back more than 4.5 times. Yet the nearest star beyond our sun, Proxima Centauri, sits over 4 light years away. Multiply that across 100 billion stars in the Milky Way, themselves just one galaxy among at least 2 trillion in the observable universe, and the numbers become almost incomprehensible. Each fact we've heard tonight, from UI Scooty's vast radius to the Sloan Great Wall's billion light-year span, underscores how utterly small and fleeting human life is by cosmic standards. Our planet, a 12,700 kilometre sphere, orbits in a system that itself orbits amid stars and black holes, all drifting through a dark sea of matter and energy. Yet in that infinitesimal speck we call home, consciousness emerged. We gaze at the night sky and map nebulae, decipher cosmic microwave background fluctuations, and send robotic emissaries to distant worlds. That paradox, our minuscule scale versus our outsized curiosity, is a defining feature of our species. Humility doesn't mean insignificance. It's the recognition that the universe is vast and ancient, that our lives are but moments in a grand tapestry. From that perspective comes wonder. Every sunrise and starlit sky becomes a miracle, a brief flash of awareness in the cosmic dark. As you settle into your pillow tonight, remember that you're part of a story spanning 13.8 billion years and countless light years, an epic still unfolding. That realization grounds us, reminding us to tread lightly on our fragile world and treat each other, and every living thing, with respect. Second, life as we know it appears astonishingly rare. Despite tens of billions of Earth-like exoplanets in our galaxy alone, we have so far confirmed only one biosphere, ours. Every water molecule in our oceans, every carbon atom in our bodies, was forged in stars and delivered to Earth by comets and asteroids. Consider Titan's methane seas, a world awash in organic chemistry, yet hostile to Earth-style life, or the iron rain of WASP-76b, where molecules vaporize under relentless heat, even where conditions skirt habitable limits, Europa's hidden ocean, or Mars's ancient riverbeds. We find clues, but no confirmed organisms. On our pale blue dot, life emerged, flourished, and evolved into beings capable of contemplating the cosmos. That singular miracle unites every human, every species. Across cultures and continents, nightfall kindles the same wonder as you peer skyward, shared curiosity that transcends borders. Our current efforts, searching exoplanet atmospheres for biosignatures, drilling into Antarctic ice for microbes, listening for technosignatures, are expressions of a fundamental drive to know that we're not alone. The answer, whatever it may be, will reshape our understanding of biology and our place in nature. Until then, life on Earth remains our greatest treasure. Protecting biodiversity, preserving ecosystems, and fostering global cooperation are not just moral imperatives. They're our lifeline to the only home known to harbour consciousness. Third, our technology has opened doors once sealed behind light years of vacuum. In less than a century, we've gone from ground-based telescopes to spaceborne observatories like Hubble and JWST, from flickering radio signals to real-time video links with distant probes. Robotic explorers, Voyager, Cassini, Curiosity, Perseverance, and soon Dragonfly, extend our senses across the solar system. Gravitational wave detectors, LIGO and Virgo, let us hear black hole mergers. Earth-observing satellites monitor climate change in real time, and private ventures aim to land humans on Mars within decades. Yet with great power comes great responsibility. Solar flares remind us how vulnerable our infrastructure is. Space debris endangers satellites that underpin global communications. Planetary protection protocols guard against contaminating other worlds and protect Earth from potential extraterrestrial microbes. As we venture farther, ethical questions multiply. How do we share resources on the Moon or asteroids? Who owns celestial real estate? What rights do future generations have to the cosmic environment we leave behind? Our tools reflect our values. By embedding sustainability, safety, and equity into mission designs, we ensure exploration benefits all of humanity. Technology is not destiny, it's a mirror of our choices. Let's choose curiosity tempered by care, innovation grounded in compassion. Finally, what comes next? Within this century, we may see permanent lunar bases, crewed missions to Mars, and robotic outposts on ocean worlds like Europa or Enceladus. We'll refine exoplanet telescopes until we image Earth-like worlds directly, maybe even detecting signs of life. Gravitational wave astronomy will map cosmic history in 3D, while quantum communications span interplanetary distances. But beyond the technology lies a choice. Will we use our expanding horizons to unite or to divide? History shows that frontiers can inspire cooperation, as the International Space Station exemplifies, or stoke competition that distracts from urgent earthly needs. The story of space exploration is also the story of ourselves, a testament to human ingenuity, resolve, and imagination. As we step into the next epoch, we carry the dreams of every generation that looked up and wondered. So what will our legacy be? Will we become stewards of multiple worlds, guardians of life's diversity across the solar system? Or will we falter, constrained by short-sighted conflicts? The answer lies in the choices we make today, in education, in policy, and in how we inspire the next wave of explorers. The cosmos awaits, but it doesn't come with guarantees. It demands our best selves, bold but responsible, visionary yet humble, driven by curiosity and guided by ethical purpose. Night owls, thank you for joining this cosmic marathon. From fiery stars to icy moons, from infinitesimal strings to immense superclusters, we've peered into realms that challenge the imagination. I hope this journey has left you with awe, perspective, and a burning curiosity to learn more. If tonight's voyage through space and thought stirred your spirit, hit like, subscribe, and ring the bell. You won't want to miss our next deep dive into science's frontiers. Share your favorite mind-blowing fact in the comments, and let me know what you'd like to explore next. Until then, keep your eyes on the sky, your mind open to possibility, and your heart grounded in wonder. This is Name, wishing you clear nights, sweet dreams, and endless curiosity. Good night, and keep looking up.